so my name is Moshe Zadka. Today I'm going to talk to you about how to make your objects more boring and why you should. Whoa, woohoo! That was exciting. Okay. My website is cobodism.com. If you catch me later, I'll explain the funny math joke that like basically 5 people can get. But it is on the bottom of everything, and you can find every single way to reach me, including Twitter and mail and Instagram. If that's how you want to reach me, that's fine. Okay, so let's try to start talking about Python and object-oriented programming. In Python, as you know, everything is an object. And not just everything is an object, right? The object model of Python is very closely related to, say, the object model of Smalltalk, where a lot of these object-oriented concepts come from. So not just everything in Python is an object. Python is really related to like these languages where object-oriented programming came from. And that's where originally people started coming up with object-oriented design principles. And why do we have them? They're basically ways to structure your code in ways that are easy to maintain in various ways. Easy to change, easy to modify, easy to debug, easy to understand. So do these design principles apply to Python? Well, yes, they come from the same source, right? They come from these languages that are very similar to Python. There's no reason why they shouldn't move. But Python has its own special flavor, its own special way of doing things. It's a little bit different. The object model is a little bit different. How it treats methods and functions is a little bit different. So most of the principles work on some high level, but applying them to Python takes some thought, and often just kind of copying and pasting what you see in like design principles doesn't work right off the bat. So I'll talk about the principles that I want to kind of tell you about how to make your objects more boring. These are the secrets they don't want you to know to make your objects boring. The first one is to explicitly declare your interfaces, to simplify your initialization, avoid as much as possible mutation, avoid hiding stuff, avoid methods, and avoid inheritance. These are all things that make your objects not boring, and you want to make them boring. So I declare interfaces. In general, the best way to cheat in an argument about Python is to quote the Zen of Python. Let it never be said that I'm above cheating. I will quote the Zen of Python. Explicit is better than implicit. Hopefully you all read Zen. You all remember that part. That applies to interfaces, right? Why not make your interfaces explicit? Instead of saying file-like object, and then we start having these weird arguments. What is a file-like object? Does a file-like object include write? Because that's a writable file object. You can say, well, these methods expect only readable file objects. Does it expect seek? Well, then you have the writable, seekable object, and nobody actually maintains it, so people write a method, and they say, this method expects a file-like object, and let you guess exactly what they use, and the maintainers of that method have not ever committed to what they need, so if they suddenly use seek, they say, well, we said you're supposed to pass a file-like object, well, we expected seek. So instead of having this weird thing where nobody knows what we actually talk about, how about we specify it in code? We make it explicit, right? So this is a good example. This is how you'd specify a sprite-like object, right? Sprites are the things in computer games that move around, right? Your character or a bullet or whatever. And this is a good way to structure a sprite, right? You'd have a bounding box, right, which says what box the sprite is inside, and then whether it intersects the box, right? It's not the same as intersecting the bounding box, because if you imagine the sprite being a circle, then the bounding box might intersect, but the circle might not intersect, right? So there's a method, there's an attribute, and you notice that you specify the method and you specify the attribute, right? You did not give any objects, attributes, or methods, because all you're doing here is just specifying an interface. Unlike, say, what you would use from an abstract base class, this is not useful as a base class, which is very good because you do not want to use it as a base class. The way to use an interface is to implement it, and the way to verify that you implement it is like that. You can literally just say, verify object, it's a method in zob.interface, and it will verify that you actually implement the interface. Of course, it's not a perfect verification, right? It doesn't check that you can call the method without raising an exception. It can't check any semantics, but it will at least check 2 things. First, the object thinks it's supposed to implement, right? This is, if you are familiar with Go, in Go they have the ad hoc implementation of interfaces where if an object looks like it's implementing an interface, it's probably meant to. No. An object will not implement an interface unless it's explicitly said, I am going to implement that interface, right? So first of all, it makes sure that the object meant to implement that interface. And in a big system where you have a lot of vaguely similar interfaces, say the iReadable file and the iReadable seekable file, it matters that the object thinks it's supposed to implement iReadable file or iReadable seekable file, and then it will actually verify it has all the attributes and all the methods that were specified in the interface. The next thing I'm going to talk about, after we understood that we have to declare our interfaces, is why we should simplify our initialization. So this is an interesting constructor. And it's interesting in exactly the bad way of interesting. There's a lot of ways this can go wrong. So first of all, it creates a new object called destination with specific parameters. And probably that object kind of like, hooks into all kinds of systems. And what if you want to mock it? What if you want to use it without the real destination? What if you want to proxy the destination to something else? You can do that because it already decided the only class it will accept is destination because it literally calls that class. So you start with patching, and that never works well because it depends on exactly how you import, and that's bad. And then, to make it even more interesting, because that wasn't interesting enough, we open a file name, right? So, of course, there's almost an infinite number of ways that the open system call can fail, right? The file cannot be there, you cannot have permission, it might be on an NFS drive, in which case it's not going to fail, it's just going to take forever, right? So you have no idea how long this construction takes. And best of all, if the destination call fails, if somehow this doesn't work, then you're left with an object that doesn't have, if the destination call succeeds and the f input, the open call fails, you're left with an object of type stuff that has a destination input, but does not have an f input attribute. What does it mean? It means if you are civilized, the way I was not here because I'm trying to match my code to slides, and you wrote a wrapper method that is useful, that shows you what f input is, that method would fail because it would try to access an attribute that doesn't exist. Now you have an object somewhere in the bowels of your system in tracebacks that cannot be displayed. That probably means that there will be a traceback you cannot display, so you cannot even figure out why open failed. So this is great, right? This is like really interesting, and you're going to have a really fun session at 4 a.m. debugging the NFS drive. And while that does cause a lot of interest, I like to sleep at 4 a.m., and that's very boring of me. So this is what I do. Right? So now the constructor is very, very boring. The constructor just copies things to other things that almost can't fail. There's really weird edge cases where some memory allocation can fail. If that happens, God help you. But if the constructor most of the time worked, but we had good code in the constructor. It shouldn't have been in the constructor, but we did make some interesting choices, right? We said that f input should be the name of a file and destination is the destination. Let's take all this code that we wrote and worked hard and kind of talked about with our teammates and decided this is the right thing to do, and put it in what we would call a named constructor. In other language, and in Python, it's just a class method that in this case has a name, right? From name, right? So you can have, in theory, other named constructor if you so desire. And it takes a class and the name, right? Which is the name of the file. And then it creates a destination. And notice that I don't bother creating the object until I have all the prerequisites of the object in hand. Which means if from name fails, then it's fine. Ideally not great, but at least I'll have good tracebacks, right? And if from name takes a long time, from name takes a long time. I can't do magic, I can't fix that, but I can figure out where it happened, right? And it's not in the weird stuff, it's in from name, I understand what happened. And there's a few things that this lets me do much better, right? First of all, I can test, right? So if I want to test this object, I can just call the constructor with a mock destination object with, say, a string IO input and do everything I do with the object. The object doesn't care. The constructor is built to support that. I'm just not going to debug from name, but that's fine. Now, from name is not very complicated code. Either it works or it doesn't. I don't have partial objects. And I even get one other nice thing, which is more and more code nowadays is starting to think, how can I leverage async, especially now that async and await are keywords in the language, and it's much easier to write async code. You'll notice that the named constructor, the way I wrote it with def. But you can easily write async def. You can make open something that, you can make like something that reaches across the internet, asks what's the name of the file I should open, then open the local file. And that can take hours, and that's fine because you'll do an await there. And that can be an async def. A constructor cannot have an async def in it, right? You cannot async def under in it. That wouldn't really make sense. What would you return? But here, an async def makes sense. It's just a method that happens to return something of type stuff. Yes? Sorry? Oh, so yeah, that's a mistake. My bad. Okay, let's move on. Okay, so you might think this is really boring, Moshe. All my constructor are gonna be like, these like that equal that, that equal that. And there's one thing that computers are really good at, which is automating the boring stuff. There's even like a book of that name, Automate the Boring Stuff with Python. And one excellent library that automates the boring stuff with Python is Attrs. Attrs helps you automate building object, and that will construct an object that is much better than the object I showed you earlier, right? Because A, it will have the right constructor, and it has a good wrapper, right? So I talked about like why I should write a wrapper, because if there's a stack trace, I probably want to know what the name of the file was, and I probably want the representation of the destination to be there. So this is great, and it also has like equality checking and a lot of other things, and it just creates auto attributes. So I just have to specify my stuff in the MyPy syntax, and it just works. And as a side benefit, I even got MyPy syntax. So again, if I was slightly more civilized, I would say destination actually has to comply with some interface, and if input has to comply with some interface. And actually, MyPy with the right plugins will support those interfaces, so you can actually be really civilized here. I was just doing it super fast. Once you use Attrs, then it's really, really easy to also make your objects immutable. So we already call Attrs. All you need to do is frozen equals true. And you notice that the way I showed you what stuff is, there's no reason to ever mutate stuff, right? The F input is F input, the destination is the destination. Maybe they, will mutate in weird ways, but there's no reason to ever mutate stuff itself. And it's pretty nice not to have to mutate it, because then you know that if you send it to a function, that function cannot mutate it, because nothing can mutate it, right? So you know that you can pass it around, and you don't have to worry about whether the function docstring says, I actually changed the F input and changed it. You don't have to read the docstring. It's not going to change it. So here I'm creating stuff, and you notice that if I try to change the F input, it will just raise an exception. So that's great, right? You think, OK, at least like you cannot mutate it. But sometimes I do need to kind of mutate, right? Imagine an object that's a point, right? Like the point has two coordinates, x and y, and you want a point that has the same x and different y. And you're not going to use that point anyway, so you say, oh, yeah, I wish I could mutate it. It would have been easier. Oh, sorry. So I already talked about that. Like immutability helps you avoid bugs. No function can change it. It helps you simplify the interfaces because usually you have to specify what invariants your class has. If you have immutability, you cannot change invariants, right? Because you have no variance, you cannot break any invariants. So whatever variance you create with will stay for the lifetime of the object. And finally, if you do want to kind of mutate, which means give me a new object with almost the same attributes except one change, there is the evolve function. And evolve is very useful. Again, imagine that if evolve is the only thing that has like the access to point, then that's fine. You'll just garbage collect the old point. But if someone did hold some weird reference to the old point, that reference is not going to change. And that's very useful, right? Like because you won't have any inadvertently share immutable data, which is, of course, the worst thing in the world. OK, so now that we've done away with immutability and we've done away with interesting constructors, why do we need private methods? So this is a classic example for private methods, right? This is an object that wants to simulate an HTTP session. We don't want to give people direct access to underscore request because then we would have to worry about what methods do we allow, and some methods have different semantics, and I might actually have different ifs, and I don't want to think about it. I just want my public interface to be get and head, and internally, they all should share some code, right, which I would all put in request, and in this case, I didn't have time to write it, and no space on the slide, so I'm just not doing anything. But in real life, this would do something HTTP-like. So what's the problem with that? That looks like a perfectly good design. Well, the problem with that is that nobody specified what request actually does, right? So what can I assume about request? What can it do, right? You'll suddenly find you need to document it, right? And you need to document it not because someone external to the class, because you're not probably the last one to touch it, right? Someone will probably want to add some post method, right? And when they add the post method, they want to care about what request assumptions request make. So it ends up you didn't save yourself any time by making underscore request private. What you did was probably not do that documentation because it's private. I don't really need to carefully document what invariant it breaks. And then the maintainer is going to have a very interesting time. And of course, you don't want any time. You want the maintainer to have a very boring time. So what do you do if you still don't want to make requests externally available? Well, you have private objects, right? We have a class called raw HTTP session. It's very obvious what they need to document about raw HTTP section, which is the request, and what it assumes. And then I don't allow access to that directly from inside the HTTP session. So my external interface is still the same thing, but internally, I built in a way that is very obvious that this is a separate object. It has its own invariants, and I should worry about those invariants. And as you maintain it, you have to read what does raw HTTP session assume. Finally, after we have done away with private methods, we come to other methods, which are not private, and we're like, should we have them? So this is a classic case of why you should have private methods, right? You have a 2D point, and you have a 3D point. And they have the method distance from origin, and each of them understand distance from origin. And as you notice, because I had to switch slides, I couldn't put both classes on the same slide because I didn't have room, right? Those classes have distance from origin, right? And this is a Pythagorean distance, but if you're a weird math geek like me, maybe you want the New York City metric, where it's how many blocks you have to go, or the max metric, or the P metric, which is really esoteric, but really important for some people. And you'll find you have more and more methods, and this is just a distance, right? Points can do a lot more things than just compute the distance, right? Maybe you want to rotate it about the origin, and you have all these things that you suddenly have to do, and your classes gets more and more bloated. Right, so it's really hard to read. And even adding one method, I couldn't fit both classes on one slide, right? That's kind of annoying. So let's stop that. Let's stop writing methods. Methods are stupid. Now we can put both classes on the same thing. But you say, well, I still want to have a distance from origin. I want to not to have to care. I don't want to have, if it's 2D, then do that. If it's 3D, do that. Great. This is why there's a module called functools, in which there's a function called single dispatch. And you can define distance from origin like that. And now you can just call distance from origin. It's a function. Notice that this code you can put in a separate module. Right? This is a separate concern. One was a concern about how to represent points. The other is how to represent Pythagorean distance, which only matters if you care about Pythagorean distance. If you care about other distances, you don't even bother importing that module, right? You can imagine that maybe it's even bigger, right? Maybe you don't even bother pip installing that Python package if you don't need Pythagorean distance, right? Maybe you only need other distances. And of course, this is just one function, but in real life, of course, this has a whole lot of things, so it might actually break out to a separate PyPI example. I'm going to skip the why should avoid inheritance, because I don't have tons of time. But we can talk about this later. If you matter, I'll be hanging out, in the conference. But I want to talk about the bigger lessons I have to talk about, about boring objects, which is in Python you can do anything. If you want to have a weird diamond inheritance and you want to have overridable constructions and that's part of your interface, you can do that. And not only you can do that, popular packages in the wild have done that, right? It's not like a theory, right? People actually done that and published the things in PyPI, and other people have used it. But maybe it's not a great idea to do that, right? Maybe it makes people's lives way, way more interesting. And why do people do that? Because when you start, you have no idea what you're doing, right? I'm on a Python channel, kind of like a secret off-the-books channel, with a lot of people who wrote like big systems, right? Like some of us come from Twisted, some of us come from Mercurial, and we all have these big systems that have all these really bad things about them. Every single thing I said is something that Twisted and Mercurial and Jupyter and a lot of these big systems you're used to in Python all do. And it's because when we started writing those big systems, we didn't know how to build big systems. We learned all these lessons later on. You cannot change a lot of the earlier decisions you make because you already made them, and now you're like stuck in like backwards compatible hell, because not only are these big systems, they're used by like everybody, right? A lot of people use Mercurial, a lot of people use Twisted, a lot of people use Flask, a lot of people use Django. Every decision that the people in these big systems made is the first approximation forever, right? So basically, this is part of our reach out effort, which is don't copy our stupid design decisions, please. Do not look at what we have done in Twisted and Mercurial. Those are all great systems built by really, really smart engineers, and occasionally I helped. But they do not show you how to write good Python code. The people who wrote those did not know how to write Python code. The way we learned how to write Python code was by building those systems. Those were where we practiced. And you don't often get these lessons until you have finished writing the big system and you have started maintaining it. So you only figure out that you've done everything wrong when you're done and these things are in wide deployment, which is why people keep making those mistakes. People say, oh, this is a great idea, and it looks like a great idea for the first year. And by the time you realize it was not a great idea, it's too late to change. Because the only way to like win the game is not to start. And so I want to encourage all of you to write less interesting code that will lead to less interesting debug sessions at 4 a.m. in the morning, because it's probably going to be me debugging it at 4 a.m. and I really, really like sleeping. So be as dumb as possible when you're writing the code so I can understand it at 4 a.m. And that's it. That's all I have to say. Do I have a few minutes for questions? OK, cool. I have a few minutes for questions. So I guess if you come up to a mic or something like that, or you can shout the question at me and I'll repeat it if that makes it easier for you. So like I said, a lot of these big systems predate single dispatch. I think by now, like some internal projects are using single dispatch. I think some big things inside Facebook. I don't know a big open source thing that uses big dispatch in general. The question was, can I give an example that uses single dispatch?
Can you explain the benefits of using evolve as opposed to mutating the object? It seems like it might just kick the can down the road.
That I can actually give a system that does it in the wild. It didn't use evolve because when it was written, Atos was not existent, but it uses equivalent code. So if you have a big system that kind of throws objects around, right, you eventually realize that you're not really sure who you gave that object to. And if you change that object, you have no idea what other piece of thing that assumes they had an object and they assume they knew what was going on is suddenly going to change. People usually think of it in terms of multi-threaded code, but the system I'm thinking about actually had 0 threads, right? Well, it has the 1 thread, but it was written in a very async style. And async style ends up having a lot of the similar things that threads have, where like these objects kind of move all about the system and they're very long-lived, and you mutate it and like you change something that is in this flow, and it really didn't expect the object to change, and now it's very, very sad. So we used, in that case, a module called persistence, which gives you like persistent data structures in Python. So like things that look like lists and dictionaries, but it cannot mutate. You can use the equivalent of evolve. So evolve is kind of like a lower grade version of that, but it's often good enough for those things.
In Python and JavaScript especially, it seems like there's this trend to shim in new things into the language that are missing. In this case especially, I feel like we saw a lot of that, a lot of decorator functions and whatnot. How do you feel like that fits into the narrative of be dumb, write less interesting code, but we're still introducing new proprietary knowledge that you need to have to understand a particular code base?
So that's a good question, and you know, like a lot of people, like they see, like you know, the first thing I start with is talking about boring objects, and then the first thing I show is the OP interface, which is a whole package that is some people consider really complicated. And it ends up that, so if you're not using ZOP interface, you're going to use other things that will be more complicated than the ZOP interface. You'll have an ABC, but the ABC, at some point, someone will add a method that does something, and you realize that this was a really stupid idea. So now you have a comment next to your ABC saying never put methods that do stuff. And then you realize that like inheriting from the ABC in general is bad, and you start having a comment next to it saying only use .register. And the thing is that like eventually you have more complexities than if you use something that people who build these big systems, right? Like in many ways, ZOP was Python's first big system, and the people who use ZOP needed ZOP interface exactly because they needed a way to manage all that complexity. And at that time, the people who were like working on Python did not have a lot of experience with big systems. So like, ABC is probably good enough. So unfortunately, like a lot of these things are missing from core Python. And you need other packages to add them. Core Python evolves more slowly than the package ecosystem. Okay, so thank you all for listening. I hope you had fun.